Welcome to the Heat Treat podcast. Today on the show, we're going to talk about ion nitriding. We have a great guest today, and I just would like to remind our mission. Our mission is to deliver news and information about the heat treat industry by experts on the subject. We will be interviewing weekly power players of the heat treat industry to discuss news, development, process, and products. All the stuff we heat treaters like to talk about that nobody likes to talk about except us. So today we have Andrés Bernal all the way from Colombia, Medellin. We're going to talk ion nitriding. Andrés, how are you?
I'm
Good.
fine, Carlos. How are you?
Good morning for you. I believe you're Central Time as well.
Yeah, it's 2 p.m. here. So, yes, Central Time.
So how's it going in Colombia? Our audience is mainly in the U.S. and they're freezing with snow. I believe you have a little more warm weather. Is that true?
That is correct, my friend. So, in the area I'm at, it's always in the 70s. So, we're in heaven here,
That 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 that's
virtually.
that's great to hear. So, I'm still planning to visit Colombia and actually go to your company whenever I have a chance. But today with the travel restriction, it's been a challenge. So it's part of the conversation. And first of all, I would like to ask you, how are you and how things are in Colombia with all this COVID?
Well, fortunately, Carlos, I'm okay. All my family is okay. The COVID thing is, it's always crazy. We feel that it's getting closer and closer. We see every time we see cases closer to our, let's say, circle. One of our engineers' dad died from COVID, actually, and some other people close to our people here at the company has also died from COVID. So it's kind of crazy. These times we are right in the middle of the second wave, so to
Right.
say, and so the ICUs are getting really, really busy. We're getting more contagious and things like that. So it's kind of complicated right now.
Actually, I saw on your LinkedIn. I know you're a great mechanical engineer, and you were actually working on a ventilator, right?
Yeah, that is correct,
Yeah.
my friend.
How did that
Uh,
go?
well, it's still going. That's a funny story because at the beginning of the pandemic here in March 21st, when we were in total lockdown from our government, we couldn't leave our houses or anything. I decided to challenge our engineering team. And I told them, all right, it doesn't seem we're going to do a lot of things this year. So let's help the society and let's see if we can make a ventilator. So we started by just watching YouTube videos, learning what mechanical ventilation is, etc. And as a matter of fact, we just finished last Friday our first in human trials
You
of our
did.
ventilators. Yes. So our first in human trials, we need to deliver the report to the regulatory agency this week. And hopefully, we'll start our second trial with a bigger sample of subjects very soon. And that has created our biomedical division, which will soon separate from the company, of course. But that's a
Right.
it's kind of it
Right.
was funny how it started, and it
Well,
ended up
if you got
in a really good way.
the engineers to design furnaces for a heat rate application, why not design on a ventilator if you have the capabilities? That's the way uh, you can actually help and support the world right now. Uh, because Andres, I have met you several times. I believe we met the first time like 5 years ago in shows,
Correct.
and you're a great engineer, right? So I'm glad our industry is actually helping create ventilators.
Well, I don't know if I'm a great engineer. I
You
just
are. You are.
I'm curious. I'm just curious about things,
You
and
are.
I have a great team. But thank you for that. But I think I do have a great team, and it all started like a something that okay, we wanted to help a short-term thing, and it ended up being a lot more complicated than we thought. Not from the engineering point of view, because a machine is a machine. It's an interface. Is control electronics, electric components, and mechanical components that obey those controls. So
You're
we have
describing a
the
furnace.
capability. Yeah, exactly. It's the
You're
same
describing a
thing.
furnace, right?
It's a machine.
Right.
So
So just a little heads up of what we're going to talk about today: plasma nitriding, ion nitriding, the difference on applications and difference from gas nitriding, the market and application for ion nitriding. Is it ion nitriding or plasma nitriding? What's the correct way to say it?
actually, both of them, and it's
Okay,
where our name, we call it plasma nitriding
plasma
everywhere,
nitriding. Okay.
but our name actually comes from the ion nitriding. So plasma contains ions, and ions are the actual nitriding. So that's why it's ion or plasma. It's okay.
So let's discuss plasma nitriding. And I'm not an expert in any means on this subject. I'm a heat treater. Uh, we have covered carburizing. We have covered low pressure carburizing, oil quench, cell quench. We have covered CQI9, NatCap. But when it comes to nitriding, everybody thinks about gas nitriding. But there's also this unique thing about plasma ion nitriding. So first of all, why don't you give us an introduction to what is the process, the main variables, what is to watch for, and you can share with the audience. I would like to remind you that the mission on this podcast is for the new generation of heat treaters to look for this video and actually get an explanation of processes of parts by experts on the subject, right? Which you are. So plasma nitriding.
Yeah, thank you, Carlos. We'll try to keep it simple. So I like to say, when I explain heat treatment, I like to say there are two types of heat treatment. One is a heat treatment in general, and the other one is a thermochemical treatment. And thermochemical treatment are those where you, by means of temperature and a different chemistry in the atmosphere, you can modify the surface of steel by introducing atoms to it, whether it's carbon or boron or nitrogen, or carbon and nitrogen together. You have a thermochemical treatment. So nitriding is a thermochemical treatment in which you introduce nitrogen into the surface of steel components. You don't nitride ingots, you nitride parts made of steel. So nitriding is a thermochemical treatment where you introduce nitrogen in the surface of those parts made out of steel. And there are different variations. There's nitriding and there's nitrocarburizing. In
What we call FNC, right?
FNC, yes, sir.
FNC.
It's called FNC because it stands for ferritic nitrocarburizing.
Right.
And the reason it's called ferritic is because it's done at such low temperature that the main structure, crystalline structure of steel at that temperature is still ferrite and not austenite. So nitrogen that gets into the surface of steel forms nitrides with iron, chromium, vanadium, aluminum, manganese, and those nitrides are hard compounds which are wear resistant, corrosion resistant. They increase the fatigue resistance of the component. So that's what you look for in
That is
nitride.
like the main application to be more the part to have more wear resistance properties, right? That's like in a nutshell what we're trying to accomplish with nitriding.
Well, yes, and also, yeah, wear is definitely something we wanna. The wear resistance is something we want to improve, but also fatigue resistance.
Fatigue.
Exactly. So a lot of things like crankshafts or camshafts are nitrided, both because it increases the wear resistance, but also because it increases the fatigue resistance of the component that's rotating at high speeds. So Yeah, wear resistant is a very important parameter when or variable when choosing nitriding, but also corrosion. I'm sorry, fatigue resistance. Yeah,
Right. We're actually going to have another episode with Stephen Christopher, which is an expert on gas nitriding.
correct.
But when talking about iron nitriding, so I believe our audience a little more familiarized with gas nitriding, right?
Right.
Because we're dissociating ammonia. But how is the process of plasma nitriding? What's going on with the atoms and particles? And everybody loves that glowing purple light, right? So
Correct.
can you explain us the magic of what happens on an ion nitriding furnace?
Okay, yes. So to be able to do nitriding, you need a nitriding given species or gas, correct? Or atmosphere or whatever it is around the part, whether it's a salt or a gas or a plasma. So let's first of all define what a plasma is. So plasma is the fourth state of matter. It's a we all learn solid, liquid,
And gas.
gases, and then when you have a gas and then you put it into an electric field or a magnetic electric field, you ionize that gas, then it's called a plasma, and it has different properties than the gas by itself. So what we do in order to be able to nitride, we need nitrogen, atomic nitrogen, not nitrogen as a molecule. And that's why in gas nitriding, they use ammonia. Because ammonia, the molecule from ammonia, it's NH3. That means one atom of nitrogen and three atoms of hydrogen. When that molecule sits on top of the part's surface, it dissociates into nitrogen and hydrogen, and that nitrogen is absorbed by the steel. In plasma nitriding, we don't use ammonia; we use nitrogen.
Pure nitrogen.
Pure nitrogen, yes, sir. But when you get pure nitrogen out of your tank or your cryogenic tank, you're not getting atomic nitrogen. You're getting molecular nitrogen. That is N2. But N2 cannot be absorbed by the steel. So you need to break that molecule. So we use plasma, that is an electric discharge from the furnace to the parts, which travels through the gas from which the atmosphere is composed.
So can you explain a little bit about this electrical discharge? Because I don't believe it's a common procedure on heat treat. Is it by an
Correct.
electrical arc? How is it
Yeah,
powered?
yeah, more or less. We don't want to have an arc. An arc is definitely a form of plasma, yes, but we do not want to have an arc. Before an arc happens, there's a lot of different stages of an electrical discharge happening. So what we do in a plasma nitrider is we place the parts inside a furnace, we connect the furnace shell to ground, and we connect the parts to minus 500 volts. So what happens is that
How do you connect the parts to minus 500
so
volts?
it's a special plasma generator. So
Okay.
we have a special plasma generator which creates the voltage difference between the walls and the parts. When you do that in a vacuum, vacuum is not a very good electrical isolator. So what happens is that immediately electrons start to travel from the cathode towards the anode, that is, from the parts to the walls of the furnace. And I'm sorry, and it creates something that is called a particle avalanche, electron avalanche, and that ionizes the gas. So there's current flowing through the parts, and there's creation of ions and different species in the plasma, which are actually accelerated in the vacuum from let's say, from the cloud to the part. Those ions actually hit the part very, very hard with a lot of energy. And that energy actually does a lot of things to the surface. For example, it cleans up the surface. It's like a sandblasting, but instead of using sand, you're using atoms.
And
You're
what's the
using
what is the temperature when this is happening at the parts?
So plasma nitriding gives you a, let's say, a wider range of temperature in which you want to work, because on gas nitriding you have a temperature in which you have to have in the parts for the reaction, for the dissociation of ammonia to happen on the part's surface. In plasma nitriding, you do that by the electrical discharge. So you can have nitriding from 350 degrees C to 650 or even 730 degrees C if you want to plasma nitride titanium, for example. So
So
it's a
pretty much you're
wide
saying
range.
it's a wide range, but pretty much under the range of gas nitriding, right?
That is correct, yes, sir.
It is. Okay. So the part is being heated by electrical discharge. Is that accurate to
Um,
say?
Also, yes, that is correct to say. There's nothing wrong with it. But there comes a difference between older technology and newer technology. Older
Okay.
technology only used plasma to heat up the parts. That is, the parts were heated by the electrical discharge. The
I
newer
see.
technology, which is the one we produce, it's what we call a hot wall. So we have heating elements around the vacuum retort, heating up the vacuum retort. So the parts are also getting some heat from the walls of the furnace and not only from the plasma. But
Mhm.
definitely the plasma is putting a lot of heat into the parts.
So mainly all the plasma heat treat furnaces are electrical heated. That's the main power of heat, right?
That is correct, yes, sir.
Okay. And so we have an atmosphere. We just say it's nitrogen, and
It's
then
not pure nitrogen, it's normally a combination of
it's a
four
combination.
different gases. Yes, sir. It's
Okay.
a combination
But
of
mainly nitrogen is what you want to have in the part. Oh,
yeah, but you don't want to have a lot. You don't want to have too much. So normally, what we use is let's say the normal composition of an atmosphere is 25% nitrogen and 75% hydrogen, which simulates the gas nitriding process with ammonia, which is 3 parts of hydrogen by 1 part of nitrogen. But it varies a lot with the different metallurgical results that we want to have. We could have 50% nitrogen, or we could have 10% nitrogen. We could also add some argon to it, and we could also add some methane to it in case we want to do FNC.
so mostly what you're saying is that mostly old iron nitriding furnaces, they have to have like a big gas tank with spam gas,
Um,
or how do they generate this gas?
so in plasma nitriding, what we do is that we have the gases separately. They're fed into the unit separately.
But you
So
have
we have
a tank for each gas. You have a tank for each gas,
yes,
and you're feeding the atmosphere with the combination of gases that you want to mix and have inside the furnace.
that is correct. So
Okay.
all the gases, each gas, like nitrogen, normally all heat treaters have a nitrogen tank outside their door.
Or a generator.
Or a generator, that is correct. And also a hydrogen. Normally it's fed in bottles. So you have bottles, you have a bundle of bottles. And argon and methane are used in such small quantities that you can only have 1 bottle of each. And that will last you for several months.
It's pretty the technologies that are, because I'm an expert on the endothermic gas, no, and nitrogen methanol.
Correct.
When it was the change from nitrogen methanol to for endothermic, the reason why this was performed was that there was a better return of investment of getting a machine like an endothermic generator rather to pay the rent for a big nitrogen tank. But there was no nitrogen generation technology. But the investment that has to be done when using a nitrogen methanol atmosphere, and I'm talking about conventional atmosphere furnaces, you need to have a massive control system for flow which is a panel with with electrical flow meters, just to control the flows on a very precise and automatic way, all by computers.
Correct.
So does this unit, they need such a level of control that requires massive control flow meters? Is there a panel in there? Do you mix them on the same pipe, or how do you control the ratios going from the tank to the furnaces?
Oh, that's a very good question, Carlos. Yes. So the composition of the atmosphere has to be very precise,
Okay.
because that will determine your metallurgical results.
To get the plasma you need, it has to be very precise, or for the.
Not to get the plasma, because even if you don't have a precise control of your atmosphere, you'll be able to make plasma around the
Right.
parts, and you'll be able to nitride. But if you have too much nitrogen, you will over nitride parts. That is, you will put so much nitrogen into the surface that you might create nitride networks and have a very, very brittle surface. On the contrary, if you have too less of nitrogen, you won't be able to nitride as much as you want. So you won't get your case depth, you won't get your hardness, etc. So controlling the atmosphere in a very precise way is very important in plasma nitriding. So the way we do it is that we have a very advanced gas panel with mass flow controllers, which our software controls, depending on the recipe that you've written and you want to run on your unit, and it controls the atmosphere to a very precise composition. We use compositions, as I said, let's say we use 20% nitrogen, 70%, 75% hydrogen, uh, a little bit of argon when we're nitriding stainless steel, or we want to go into deep holes or things like that. We use a little bit of argon, 2%, for instance, or 5%, or even 30% when we want to really sputter clean stainless steel at the beginning. Or we can do FNC with a 3% methane. So the atmosphere needs to be controlled very, very precisely, and we have a very advanced gas panel for that.
Right. So after you have the atmosphere inside the furnace, and the chemical reaction going on with all the plasma and ions that we just talked about, do you take a sample from the atmosphere and you measure it on a gas analyzer outside the unit?
No, we don't do that. That is a good question, and one of the let's say that is one of the advantages of plasma nitriding, that the atmosphere composition, the controls that we use when we put the different gases in it, is so precise, based on the mass flow controllers, that we know the exact composition of the atmosphere and how the reaction is happening. In gas nitriding, for example, a lot of the reactions that are happening inside the furnace depend a lot on thermodynamics. That is, on how ammonia dissociates before and after, or how much of surface area you have inside the furnace.
That's like the big thing, like the DA, the dissociation of ammonia. That's like the big thing. Everybody talks about it when you talk about nitriding.
Correct,
Yeah, gas
because
nitriding. Sorry.
Correct, because the ammonia that is actually available for nitriding in gas nitriding is actually the ammonia that has no dissociated. So those thermochemical reactions are kind of complicated to control. Well, now it's more easy with the newer controls, and they take a sample and then they measure it. But you don't need to do that in plasma nitriding. It's very much what you put in with the mass flow controllers, which is very controlled, and that's what you get.
And what's like the main variable on ion nitriding? When we talk about atmosphere or carburizing, we wanna measure carbon potential. When we talk about gas nitriding, we're talking about dissociating ammonia. What's like? Is there like a plasma potential or a plasma? I don't know, a composition of the atmosphere. What's like the main variable that you track besides just temperature and time?
Well, there are a bunch of them. And this is where sometimes it gets a little bit complicated for people to use plasma. And this is one of the, let's say, disadvantages of the technology, that there's a lot of variables that you need to control. Uh, but our nitriding potential definitely depends on, first of all, the composition of the atmosphere. That is how much nitrogen you have in the atmosphere compared to the rest of the gases. That is, do you have 25% of nitrogen? Do you have 40% of nitrogen? Do you have 60% of nitrogen? And as I said, that is very controllable by our gas mixture. But then there's a lot of there are other variables like the voltage,
Voltage, okay?
pressure.
Pressure.
What's the pressure you have inside?
Atmosphere pressure, you mean?
Yes, the pressure in the atmosphere, because even though plasma is created under vacuum, but even though we work under vacuum, we still put some gases in it. There's no such a thing as a perfect total vacuum. It's a partial pressure of gases at around, and the process runs between, let's say, 1 and 10 torr. So partial pressure of gases is a mixture of nitrogen, hydrogen, methane, and argon, depending on the recipe.
And what's a typical cycle time for ion nitriding? Is there, it
Typical,
has to be a vacuum first, and you have to purge the chamber with nitrogen, and then
that is
elevate,
correct.
and then elevate temperature and the soaking time. Can you explain a little bit about the cycle, what's
Yes.
going on? Is there a phase, different phases? Just for the audience, and I'm learning a lot from this conversation. So
Great.
this is what I love doing
I
podcasts.
hope so.
I don't know if I told you, but when I began doing this, I since we were isolated and we just had Zoom calls, I decided that I was going to talk with everybody I knew, just to just as a general conversation. And every time you talk with a heat treater, conversations gets pretty technical because we're very passionate about our industry, and you learn a lot, right?
Yeah.
So I just told to myself, I can record this, upload it, and this information is really valuable to all the generations, to the new generation, right? So this is exactly what we're doing. So sorry to
No,
just
it's all right. It's all right.
oh,
You're doing a great job,
I
man.
just projected myself. So
It's okay.
phases, cycle time, just like a standard recipe
Okay.
uh,
So
for
it all
ionized training.
starts, yeah, it all starts with evacuating the chamber
That's a,
to
a
what,
purge.
well, it's not a, what we call a purge is backfilling the chamber up with nitrogen. But the first thing we do is evacuating the chamber. So we pull down vacuum to our base vacuum level,
With a
which
vacuum pump.
with a vacuum pump, yes, sir. We
Okay.
use a combination of a dry vacuum pump with a booster. So we evacuate the chamber down to 0.05 or 0.02, um, and and then we purge it back with nitrogen, and then we evacuate it again and start the heating elements outside the retort. Once the parts have preheated to about 200 degrees C, then we start the plasma. We turn on our power supplies. We make that electrical discharge on the parts. And while the parts are heating up to the process temperature, we take that time and we call it a cleaning cycle or a spotter cycle. As I said, the plasma is an ion bombardment of the parts, and it will, let's say, blast the parts with atoms and ions and clean, microscopically clean the parts before they are nitrided. So it actually sputter off all the oxides, greases, except all the oils, etc., all the dirt from the parts. And so it's ramping up to process temperature. Once we get to process temperature, you can either, in, let's say, keep the process running with cleaning, which is normally a bigger, a combination of hydrogen and a little bit of nitrogen and argon. And then you start the cycle. The soaking
So,
time, the
so,
nitriding steps.
so we can say that until this, we're preparing the chamber to ion nitride, right?
We're preparing the parts.
The
We're actually
parts.
cleaning the parts in
We're
the same furnace, in the
got it.
same process.
So, what's the time frame since you close the furnace, you pull out wherever it's inside with the vacuum pump, and you raise the parts to temperature? What's the time frame?
So it normally takes about 2 hours, depending on the furnace size and the size of the load, of course. But it's anywhere from 2 hours to 5 hours.
Okay, just the
Uh,
ramping and the setup of the right
and the
atmosphere,
cleaning,
the cleaning.
yes.
Okay, got it. Got it. That's
Let's
all.
say not
That
the setup of the right atmosphere, because the atmosphere just changes like that, just
okay.
in a heartbeat. It
Okay.
changes very rapidly with the mass flow controllers. But we do, while ramping up, we do a preparation of the surface. That is, we clean up the parts from oxides and greases and oils, etc. Like, again, like a sandblasting, but instead of using sand, we're using atoms. Once we get to temperature, then we modify the atmosphere to the nitriding step. We modify the voltage, the pressure, whatever it is that we want to do according to the recipe that you've written. And then you run the nitriding cycle. Nitriding cycles go from half an hour for high-speed steels to 60 hours or 72 hours, whatever it is that you, depending on the case depth and the type of steel that you want to do.
Right.
Let's say,
Hopefully you do it right when you go, say, 60 hours, right?
that is correct.
Right.
But I mean, a very standard process lasts from 10 to 15 hours.
10 to 15.
Yes.
That's included with the prep time of the 2 hours to set everything up, or just the nitriding process itself?
Just the soaking, the nitriding,
The nitriding.
just the
Okay.
diffusion of
So
nitrogen inside steel. Yes.
10 to 20 hours. It's common,
It is
right?
very common. Yes.
Okay. Okay.
Very, very common.
Okay. And here comes an interesting question, and I believe you will be you will have a great answer. But when you have a customer, because you sell furnaces, right? How do you size a furnace, and what do you need from the customer? Because sometimes the customers always give you the information that they have, but they can be very vague because the project might be not landed yet. So tell us about this sizing of the furnace procedure. What's the standard? This can work for any furnace, right? Because you need volumes, types of steel, cycle times. How do you like to size a furnace?
Well, first of all, we request some drawings from our customers. Normally, in these drawings, we can find, of course, the geometry of the part and also the nitriding specs. That is,
The material type.
Yeah, exactly. So what grade of steel are we talking about? And what are the nitriding specs? That is the case depth, hardness, white label, specifications, etc. Once we have that, we can determine what, based on our experience, because I'm going to rewind a little bit.
You can rewind
iron heat.
anything you want.
Thank you. Iron heat is actually a spin-off from a heat treater. So we're originally commercial heat treaters. My dad started a commercial heat treat shop 40 years ago. And I worked at that heat treat shop until we created Iron Heat.
So you're a heat treater, born and raised.
Yes, sir. I'm a heat treater.
Right.
I've been going to the heat treat shop since I was 8. So once we have, based on that experience, once we have a parts specs, we decide what's the cycle time, what are the parameters. So we say, okay, this is going to run at 500 degrees C's, and it's going to run for 24 hours nitriding cycle. And okay, what's your production size? That is, how many parts a week do you want to run? Do you want to run, or how many parts a day, or how many parts a month do you want to run?
A question. Let me stop you there. So one of the beauties of vacuum furnaces is that when you have parts, when you don't have parts, you're not using energy. That's a very big con about IQ furnaces, because if you have half the utilization of a furnace, you need to keep it uh, at working temperature, right? And you're still consuming gas. So on ion nitriding furnaces, when you're not running parts, you can have the furnace uh, at a regular temperature, right? It's not like you have to keep the furnace always at very high temperature. I lost you there.
I'm sorry. Yeah, I was muted there for a minute.
Well, you know what
Oh,
I mean is that you're not using energy whenever you're running parts.
that is correct.
It's a great pro for foreigners to have.
Well, it is a plus and a minus because you're heating up the furnace and cooling down the furnace every time you're running a part.
And you're gonna
But
have you're gonna have distortion, right? And the furnace is gonna wear it out a little, right?
no, it's all right. I
No,
mean, it's such a low temperature. But furnaces in plasma nitriding are not self-destructive machines.
they're
Just
not.
like yeah, not
They're not?
as IQ furnaces. Not
That's a
they're not.
that's a big pro. That's a
It
big
is.
pro.
It is. It is. It is a big plus. Yes. So once, let's say, once we've decided what the cycle is and how many parts a customer can put into that furnace, then we can tell them what size of a furnace they need, and then give them a quote.
Fantastic. So
That's how we can do it. Yes, sir.
yeah, well, sometimes customers, they only have half of the picture from their customers, right? So
Correct.
they'll give you what they have at that time to work with. So, and
Correct.
well, this is one of my favorite parts of the show. So I always ask the guests for a heat treat hack. You know, hacks are something which are right now trending. You know, life hacks and in industry hacks. But if you were to give us a heat treat hack, what will it be?
Well,
You know, heat treat hack or heat treat gadget. You know, we're
yeah,
gonna I believe we can add that to the show. Heat treat gadget. But you know, let's start with a heat treat hack. Sorry, I put
well,
you on the spot.
it's all right. Huh? It's all right. Well, one for nitriding, I would say. I always tell people there are four reasons why parts distort during heat treatment. There's the first one is thermal shocks. When you quench a part from high temperature, you're creating a lot of thermal shocks in the part. The second reason is because of phase change. So when steel goes from ferrite to austenite and then to martensite, there's a lot of transformation because the specific volume of each of those phases is different from each other. The third reason is because there's stress relieving. When you machine a component, there's a lot of stresses built into that component. When you go and heat it up to process temperature, the part stress relieves. And how does it do that? By changing form, changing shape. So it deforms. And the fourth reason is because there's mass changes. When you do carburizing or nitriding, you're actually introducing atoms. So you're actually changing the mass of the component. Well, for nitriding, you can eliminate the first two. There's no thermal shocks and there's no phase change. So you only have two reasons why a component may distort during nitriding. Uh, and the most important of those two, and it's probably 95% of the reason why parts distort during nitriding, is because of stress relieving. So people always say, okay, how do parts change shape during nitriding? Yes, they could because they're being stress relieved during the nitriding process. So if you don't want to have any distortion on your parts, you better do a rough machining, stress relieving, fine machining, and then do your nitriding, and then you won't have any real deformation on your parts.
So there you have it from Andrés Bernal, your heat treat hack of the day, right? And I love this part of the show. Well, and Andres, now let's get a little more, more informal. So Um, how did a Colombian heat treater became or unfounded I'm heat and started saying, I'm going to do plasma furnaces, right? Because you were a heat treater. I don't know which processes you run at your dad's heat treat, right? Uh, just tell us about it. How do you evolve to be who you are today? Which I said earlier at the show, you're a very smart engineer, right? And just talking to you, I can confirm that. So you just tell us a little bit about it. And while you're doing so, uh, the last part of the show, I always ask our guests as well to give us a personal advice or experience that could actually help the new generations of heat treaters. What would you like to be told uh, 20 years ago from a guy who actually had some experience? When you started your career, if you could go back on time and tell Andres when he was 15 years when he was 15 years old, what would you tell to yourself?
Okay, let me start with the first question. The answer is a little bit funny, and I've told some people about it already. So I was working on my dad's heat treat. My dad's has always been this innovator. He's also a
That
mechanical
the
engineer.
heat trees in Medellin, right?
That is correct, yes, sir.
Okay.
There are actually three plants from that heat treat shop. We have one in Medellin, one in Bogota, and one in Lima, Peru.
Okay.
I was at my dad's heat treat shop. We were working there. My dad's always been an innovator. He's also a mechanical engineer. And we wanted to do nitriding processes. So we only had three choices: salt bath nitriding, or salt bath nitrocarburizing, which is actually the most common process. There's gas nitriding, and there's plasma nitriding. We didn't want to have any salt bath nitrocarburizing because it uses cyanides, and we didn't want to have that at the shop. Uh, Gas nitriding was another option, and this is funny and sad. Ammonia, how people steal ammonia to make drugs and things like that. It's
Yeah.
also happening in the
Right.
States. Well, ammonia is a precursor for doing cocaine, so it's not so easy
Okay.
to get in Colombia.
And you're and
You
you're
can
and you're in
imagine
Colombia,
why.
right? Right.
Yeah.
I
So,
can't. I can't. Is there a particular reason?
no, I don't
No,
want to talk about that.
no,
But
no,
anyway,
no. I mean, it's yeah.
uh, so gas nitriding was not an option for us either. Uh, Plasma nitriding was, but then I can only recognize three important companies making plasma nitriding, high-end plasma nitriding equipment, and the three of them are based in Europe. And the Colombian market was so small; it's still very small for heat treat shop. It was so small that if we bought the equipment, we would have never been able to pay it off
The
because it
ROI.
was just too expensive for us.
Okay. Okay.
So our company is a small company. I
So,
mean,
so
we
what
have,
what is the market in Colombia? It's construction mining. I know Peru is big on mining.
yeah, it's very much just replacement parts. So there's
Replacement part.
no OEM making anything
Okay.
really. So there's no like we can go to an OEM that's going to give us a production of 100 parts a day of certain part. No, we just make one part. We just make one gear. Somebody's machine broke down. They have
Okay. Okay.
a shop machine a gear, and then they bring the gear. We heat treat it for them, etc. So it wasn't worth it for us to buy the technology. So we decided to go ahead and develop it ourselves. So I did a lot of research, called a lot of people around the world.
How old were you?
Well, I started that research back in 2008.
Okay.
So that wasn't so long ago. Um, and 2 years later, we had developed the technology. We started using it, our own heat treat shop. 2 years later, after we had been using it, we knew what we wanted to improve, what we wanted to change. And we've been doing a continuous improvement process ever since. So that's how we ended up making plasma nitriters. Then we decided, okay, why don't we want to go out to the world and say, hey, we can do this.
Right. You had a product,
We had a, well,
a proven product.
yeah, we had a prototype which we needed to improve, and we've been doing it ever since. And I can finally say that we have a very good product. We can compete with any other technology of plasma nitriding in the world.
Yeah.
So that's how we became plasma nitriter people.
And going to my question. So you say 2000 and what when you started
8.
8, okay, so we got around 12 years now. So if you could go back in time and tell Andres, the young engineer, something, what would you tell him? What would be your advice for him?
Oh. Well, you know what? I'll tell any engineer that whatever you want to do, you can do it. You have to put a lot of hours in it. You have to put a lot of effort. You have to sacrifice a lot of family time and things like that. But if you really want to do it and you want to go out in the world and compete, you have to do it right. You have to want to be the best. You cannot just go out and do something just for the fun of it. And I mean, if you want to really make something out of it, like we're finally doing, you have to want to be the best because that'll give you a lot of satisfaction and love for what you do. And that's what we want. We want to be the best,
Very
and that's
passionate
why
words.
we keep improving.
I can look from here that you love your profession and you have a passion for the industry. You know,
Yeah, I do.
Yeah, you bet. Plus, you meet a lot of interesting guys that also had share the same passion for the industry when you do the kind of stuff. Because I assume you most of the time you spend it's either engineering or sales, right? Is that accurate to say it?
That is correct. Yes, sir.
Right?
That's
Okay.
accurate to say.
Well, that was Andrés Bernal, the power player of Ionite Trading, all the way from Colombia, Medellin. Andrés, I hope this is not the last time we speak on the podcast. This was great enlightenment for me. I did learn a lot. Just would like to tell the audience to subscribe to the channel. This is being uploaded on YouTube, on the History channel. It's on Spotify, the History channel, YouTube, and LinkedIn, right? So every week we're going to be posting an interview with a power player of the industry, and he's going to give us a great class like Andres Bernal just did. So, Andres, all the best to your team and yourself, all the way to Medellin, and hope to talk to you in the next couple of months. And I hope to see you in the shows, right? After all of this is over, right? But right now, it's been a great podcast. Thanks for sharing all your knowledge with us. Uh,
Yeah,
Thanks for
thank you,
being in the show.
Carlos. Thank you, Carlos, and congratulations on this podcast. I think it'll be a great thing.
It is, so you can watch it. So have a great week, audience, and keep treating stuff.